let's finish off talking about probability by bringing together a lot of the different things that we've talked about under the umbrella of one example. Let's say we're tracking the return on investment of a certain type of portfolio, and we've modeled it as a continuous random variable. And the thing we know is we've computed an approximation for the cumulative distribution function. Now, in terms of the cumulative distribution function, you should be able to very quickly and easily write down an expression for all three of these things. Why don't you take a second, pause this video, and write that down. So the probability that our random variable will be less than 1%, well, that's exactly f of 1%. One thing to remember is we don't have to worry about less than or equal to, because this is a continuous random variable. Number two, what's the probability it'll have a negative return on investment? Well, that's the probability that it's less than 0, so that's f of 0. What's the probability it'll have a return on investment greater than 10? Well, the probability that it's less than 10 is f of 10%. So the probability that it's greater is everything else. So 1 minus f of a tenth. 100% of the time minus the times that it's lower than 10%. From the cumulative distribution function, I can compute the probability density function. Take a second, remember how we do that. The probability density function, which we usually call little f, is the derivative of the cumulative distribution function, big F. For the expected value, we take the integral from negative infinity to infinity of x times f of x. Of course, in this case, this is the integral from negative infinity to infinity of x times the derivative of big F dx. These are the same. And we can also remember the definition of variance and standard deviation. So the variance is the integral from negative infinity to infinity. It's something like an expectation. It's the expectation of something. So we need to multiply by the probability distribution function. And the thing we're taking the expectation of is my value minus what I expect my value to be squared. And the standard deviation, which we denote with a sigma, this top one was the variance, or I suppose we're calling it R. The standard deviation, which we call sigma, is just the square root of the variance. So if you were given something for the cumulative distribution function and you wanted to compute these, you would have to sort of do them in order. So the last page, we could just use the cumulative distribution function as it is. For the probability density function, we'd have to differentiate. And then we would use this thing we got to find the expected value. And then we would use the expected value to find the variance. And then we would use the variance to find the standard deviation. Let's do a quick interpretation. So last year, let's say your return on investment was 1.25%, and you're trying to figure out how that compares historically. Is it a good year? Is it a bad year? Is it an average year? You've calculated your expected value. So this is like your average. So your average is about 1%. So you're a bit above average. But is it a lot above average, or is it a little above average? In order to put things into perspective, that's where we like to use the standard deviation. We think of standard deviation as average distance from the average. If we're thinking of it this way, then a sort of average year, we can imagine, well, it's between 1% plus the standard deviation and 1% minus the standard deviation. So if I think of 1 as the average, my sort of average amount of wiggle room is 0.75. So if I add 0.75, I get to 1.75. If I subtract 0.75, I get to 0.25. So if you want to think of the average as a range, what's the range that things mostly fall into? This is a way that we like to sort of interpret the standard deviation. So we're a bit above average, but not an unprecedented amount. If we were at 2%, that would be a super good year. 1.25% is within a standard deviation of average, so we would call that a fairly average year.